Hi guys, Mrs. A here. Today we're looking at solving polynomial inequalities. So to have a polynomial inequality means that we have a polynomial expression with an inequality sign, so it could be greater than or less than. It could have the equals attached to it as well, with the something else on the other side. So in this case we have one number. It could be another polynomial as well. So when we have this kind of a situation, we want to treat this in the way that we would treat it if it were a polynomial equation. So if we had a polynomial equation here, meaning instead of this greater than sign, we would have an equal sign there, we would go ahead and follow a process to solve that equation to get the zeros of the polynomial. We're going to do the exact same thing, ignoring that inequality sign and treating it like an equal sign for now. So that's going to be the first step of this process. So when we solve for the zeros of the polynomial, we need one side to be equal to 0. We're going to take this 10 and subtract it to bring it over to the other side. When I do minus 10 here, I have to do it on the other side, and you'll see that the plus 10 minus 10 cancel like this. In this case, and we'll have 0 on the other side. So let's rewrite what we're left with. X cubed plus 11x squared plus 18x is greater than 0. So this is what we have now. Now we're going to go ahead and factor this polynomial. So there are different ways to factor the polynomial. You have to determine the method that you're going to use. It is a degree 3 polynomial, so in some cases we might use the factor theorem and do long division in order to factor it, but in this case we see that we do have a common factor of x, so I'm going to pull that x out. So I'm not going to need to use long division of polynomials for this particular question, but for some of them you will have to. So when I take out that x, I am left with x squared plus 11x plus 18 is greater than 0. Okay. We have now this quadratic in the brackets. We need to factor this polynomial. It's a simple trinomial, so I'm just going to use our product and sum method. So our product is 18 and the sum is 11. The two numbers that we're going to choose then are going to be 2 and 9. Okay, so we're going to place in our factors x plus 2 and x plus 9, and all of this is still greater than 0. Now that polynomial we had on the left hand side up here is fully factored. You see we have 3 distinct factors. From these 3 factors we get our 3 zeros. So far this has been exactly the same as solving a polynomial equation. So we get our zeros from these factors as we normally would, like this. Okay, so up until now this is the same as what we're used to with polynomial equations. Now we're going to do the process for solving the inequality portion. So we want to know, when is this polynomial greater than 0? Meaning, when is this polynomial function more than 0, or when is it positive above the x-axis? We're going to use an interval chart and do some test points to figure out when the function is greater than 0. So when is it positive? To start off, we want to see the intervals between each one of these zeros. So the easiest way I find for you to do this is to use a number line. Make sure that we put those zeros in the proper order. So I'm going to do a rough number line here like this, and we'll place our numbers. The first x is 0. We have a negative 2, which would be about here, and we have a negative 9, which would be around here. So those are our 3 zeros. From those 3 zeros, we get 4 different intervals that we're going to need to test. So we need to test when x is less than negative 9. We're going to need to test when x is between negative 9 and negative 2. We'll test when it's between negative 2 and 0, and then we'll test when x is greater than 0. So we have 1, 2, 3, 4 different intervals that we have to include in our interval chart that came from those 3 zeros that we found from the factored polynomial. Okay, so now let's set up the interval chart. It looks different for different people. This is the way that I set it up, but you might see different variations of this. So our intervals are going to be when x was less than -9, when x was between -9 and -2, when x was between -2 and 0, and when x was greater than 0. So I've written all of those intervals in my interval chart, and I'm just going to separate them so it's a little easier for you to see what's going on. Okay, that'll do. Now we want to choose an x inside of each of these intervals as our test point. The x you choose does not matter. As long as you choose a number that fits within each interval in these columns, you're going to get a positive or a negative result on no matter which x value you choose, because the zeros are what separates the function from being positive and negative. So I'm going to go ahead and choose the easiest numbers that I think we can do in our head. So I'm going to choose -10 here. I'll do -3 for this interval. For this one I'll do -1, and for this one I will do +1. Okay, now we need to test the value of the function of that polynomial for each of the x's that we chose. So we have to do just some quick mental math here with each of our factors when we sub in the x values. The value of the function at each x value is not what's particularly important to us. It's whether or not the function is positive or negative at this x value. So we don't actually have to do the full calculation. We just have to worry about positives and negatives. So when I plug in -10 here, the x will be -10. And then -10 plus 2 is going to give me another negative number. And then -10 plus 9 will give me another negative number. So we will have a negative times a negative times a negative, which produces a negative result. And that's all we're really interested in for our interval chart. Let's do it again with the -3. So I'm going to plug the -3 into that factored polynomial. I'll have a -3 here. -3 plus 2 is still negative, and then -3 plus 9 is positive. So we'll do a negative times a positive, which gives us a positive result. Let's do the -1 now. -1 here, then -1 plus 2 gives us a positive number here, and -1 plus 9 gives us a positive number here. So we have a negative times a positive, which is a negative result. And the last value, +1, well, if I plug in 1 here, and 1 here, we get a positive times a positive, which is a positive result. Now we can find the intervals that satisfy this original polynomial inequality that we were given. So the original question asked when was the polynomial greater than 10. We rearranged it to be this polynomial greater than 0. So now we're going to find all of the intervals in which the polynomial is greater than 0. So when is that polynomial value positive? Well, it's very simple to do that. We just look at the values that we put in the previous row. So here, is the polynomial greater than 0? No, it's not, because it's negative. Is this polynomial greater than 0? Yes, it is, because it's positive. Here, on this interval, it is not greater than 0, and on this interval, it is greater than 0. So the answers, the solutions for this particular inequality will be where we answered yes. So we have this section and we have this section where we answered yes. So we can write down our final solution then. Therefore, the solutions for this polynomial inequality would be when x is between -9 and -2, or when x is greater than 0. And I'll just point out one more thing here. We have inequality on our inequality signs in these intervals. We do not have an equals on any of these because in the original question, the inequality sign did not have an equal on it. So if it were greater than or equal to, then our solutions would also need to have the equals because these zero values are what make the function equal to 0. So in this case, there are no equals on the interval solutions. Thanks for watching. Mrs. A Loves Math.